Okay, welcome to the introduction of solid state physics. So I'm going to begin my lecture at noon sharp. So please take your time for the upcoming 10 minutes. So I will be back soon. Okay, hello everyone. I guess all of you can hear my voice clearly. So if you have any technical issue, please leave your text message on the chatting window, and my teaching assistant will help you. So make sure your microphone and web camera have turned off, and if necessary, I'm going to give you some right to speak up. Going back to the first slide for today's lecture note. Okay, just in case. This PowerPoint and my voice will be recorded together. So I guess since I'm going to post, I should download this movie clip from cloud. So it will take a few days to post my recorded lecture into iCampus. Okay. So I guess all of you have learned some doping, what the doping technique is. So today I'm going to tell you some more details how to understand dopamine atoms can be activated electrically and how those dopamine atoms are illustrated in the energy band diagram. So let's begin. So in lecture note number 5, I'm going to tell you some important constants and the energy band models as we have learned in previous slide. And we will revisit the physical meaning of thermal equilibrium. Afterwards, Fermi-Dirac distribution will be studied, including Boltzmann approximation. Lastly but not least, we're going to study the relationship between Fermi energy level E sub F and electron concentration and hole concentration P. So please try to read the section 2.4 in chapter 2 of the textbook. So in this lecture, I'm going to use tons of symbols to indicate how much the unit charge value is. So I guess I strongly recommend you to remember all those specific number. Okay, then it will make your life much easier. So here, let's read out. Unit charge is small q is 1.6 times 10 to the minus 19 coulomb. So please remember it. And the permittivity of free space, epsilon naught, is 8.854 times 10 to the minus 14 farad per centimeter. So farad is the unit for capacitance. And Boltzmann constant K, 8.62 times 10 to the minus 5 electron volt, which is equivalent to the unit for energy, joule, and over Kelvin temperature. And Planck constant Ha, not H. Please say it Ha. 4.14 times 10 to the minus 15 electron volt times second. And mass of free electron, a single electron, how heavy it is. Well, the answer is m sub naught is 9.1 times 10 to the minus 31 kilogram. And lastly but not least, you should remember this number. This is very important number in device physics. If you don't know this value, kT over Q here, then maybe you should not become the professional in the field of device, semiconductor device. So kT over Q, okay? kT over Q at room temperature, okay? Always kT over Q is 26 millivolt, okay? If I'm asking what is the value of kT, then simply 26 milli, and this Q go back to the right-hand side and the electron volt, okay? So kT, the unit of kT is equivalent to the unit of energy, okay? So herein, just for your information, 1 electron volt is equal to 1.6 times 10 to the minus 19 joule, okay? So remember, those are some very important constants to understand how electrons and holes are moving around within a silicon crystalline material, okay? More specifically, if you would like to try to understand how DRAM and NAND flash is working, how to store data in a silicon material, you should understand, figure out the memory, have your own memory, the value for all the important constants shown in this slide. Okay, so make sure to remember all those numbers. Okay, let's move on to the next slide. So I guess a few students have some technical issues, I guess, but no worries because I'm recording all the lectures, so you should catch up later. So no worries too much. But I guess the headquarters of this university has asked me to double check your attendance online real time. It doesn't make sense anyhow, but that is the rule. Rule is rule, so we should follow it. Anyhow, my TA is now checking your student number ID and name in chatting window. So please make sure your user ID is student ID and your name. I guess all of students have well done, so no worry, not too much. So, and since this is the very first lecture as a real-time lecture, so if you have any technical issue, I'm going to take all the excuses. So not too much worry about. Okay, let's move forward. Next one is dopant ionization drawn in band model. So in the previous lecture, I explained what is the band diagram is. Okay, but in this slide, let's figure out how dopant atoms are ionized electrically And those processes are drawn and illustrated in energy band diagram. So on the upside, figure A, this solid black colored line indicates a band edge of conduction band and as well as a valence band. So east of C and east of E are there. And here the dotted line indicates, the energy state or donors, right? Because it's EC minus ED. The energy difference, EC minus ED, is indicates ionization energy for dopant atoms. So in this case, the type of dopant is donors, and since at not room temperature, but at 0 Kelvin, everything is frozen out. So the dopant atom has been well bonded to the silicon atom. The situation is like this: a given silicon crystalline material, suppose that this silicon atom is replaced with phosphorus, which is the atom coming from the column 5 in periodic table, so that is the total number of outermost electron is 5. So fifth electron is still well bonded to the phosphorus atom at 0 Kelvin. However, once temperature increases, a few of fifth electrons becomes loose. The bonding between this fifth electron and phosphorus atom becomes loose and broken, so that these two free electrons will become free. In other words, the bonding between this electron and the phosphorus atom will broken, so that in Anna's band diagram, that breaking process will be illustrated like this. Okay, and 2. So this breaking process will be happened here and there across the silicon crystalline material. So this figure looks, looks okay. So as temperature keep increasing, and if we approached the room temperature, say is 300 Kelvin, then all the dopant atoms from here 1, 2, 3, 4, 5, 6, 7, 8. So as shown in this NH band diagram, total 8 donor atoms are fully ionized. What did I say? Fully ionized. So suppose that at room temperature, all the dopant atoms are fully ionized. Then how to describe or how to draw this process in the energy band diagram? Well, the answer is quite easy. Just draw all the electron, fifth electron. This indicates a fifth electron coming from, for example, phosphorus. Okay, phosphorus number 1, and this is also the fifth outermost electron from phosphorus. I guess number 8. So all the fifth electrons are broken out, so that we obtained 8 free electrons coming from 8 dopant atoms. So previously I told you the number of free electron concentration, this small n indicates how many free electrons are available for unit volume. Okay, so small n should definitely equal to the dopant, the total number of donors, right? This n sub d indicates how many donors we have per cubic centimeter. Okay. N is n sub d, but herein, to put more emphasis, all donors are fully ionized. To write down n is equal to n sub d, which is also equivalent to the nd plus. Okay. Just in case, so how come plus? Because the donor atom has lost its fifth electron, so it will become positive. Okay. All right. So that's a basic, process, how to draw and illustrate, the fifth electron has been broken away from the phosphorus or arsenide or dopant atoms, and all these steps are well drawn in an energy band diagram as a function of temperature. Okay, so at 0 Kelvin, all the dopant atoms are frozen out. Technically speaking, all the dopant atom is not ionized at all. Okay, but at room temperature, we assume that 100% of dopant atoms are ionized. In other words, full ionization is a basic assumption to understand and to estimate how many free electrons are obtained from the dopants. Okay, so why doping is very significant in silicon device? As a device engineer or process engineer to fabricate 1Z third generation of DRAM product. Suppose that you're a process engineer and your boss has asked you to implement 10 to 10 to the 15 free electrons per unit volume. What is your solution, engineering solution? Well, definitely, if you'd like to control and modify the total number of free electrons within a silicon crystalline material, and always think of doping technique. So doping is very perfect in terms of the modification and controllability of total number of free electrons. So the total number of dopant atoms is always equal to the total number of free electrons that you can handle. Okay, so now let's move on to the next one, bottom side one. You can see that another energy band diagram on the bottom left-hand side here, conduction band edge and valence band edge. And here a few dotted lines are available drawn, and that dotted line indicates acceptor's energy state. Okay, at 0 Kelvin, all the energy state for acceptors are empty. So there is energy state, which means a certain electron can take in. However, at room temperature, not at 0 Kelvin, no electron can take in. However, as temperature increases, even at room temperature, all the energy states for acceptors are filled in with free electrons. Where are they coming from? From where? So the answer can be found in the figure shown in the middle. Look at here, the electron coming from the valence band. So previously I mentioned that all the valence bands are filled with many electrons. What kind of electrons? Which electrons are filling out this valence band? The answer can be found on the top side here. You can look at these covalent bonds. All those covalent bonds, are formed with electrons coming from the silicon atoms, right? So by sharing two electrons for this specific, covalent bond, we can build up the solid state crystalline silicon material. So all these electrons in valence band comes from the covalent bond. But here, interestingly, a single electron has now tried to try to get in this empty energy state. Why? Again, the plus y direction in energy band diagram indicates energy of electron. So once electron is excited up, or if for some reason electron which is originally participated in a covalent bond between two neighboring silicon atoms, has been heated up, then it should take the energy state, which has a slightly higher energy level. So originally, this electron has this amount of energy value. But now, this electron is excited up, heated up, so that the energy of the electron is this. So certain amount of energy has been observed by this electron. What will be happened? Originally, the electron was here, okay, to build up the covalent bond. So it is very stable, and you can say that it exists at a slightly lower energy state. However, once this electron has become free or any available seat, then it will be excited up in terms of energy. So, as we have learned, the electron hole pair EHP, the concept of EHP, uh, the electrons in pure silicon material requires, band gap energy 1.12, always called number 112. However, once a pure silicon material is doped with many acceptors, those acceptors will create these empty energy state. Then you don't need those too much energy to have free electrons in crystalline material. Very small amount of energy. What is that quantitatively? See this dotted line energy level is E sub A, and the balance band edge is E sub V. So if you have a E sub minus A over EB energy difference, then your covalent bonds can be broken. So how come that kind of steps and that kind of process can be happened? Because of the acceptors that you have injected. Okay, so without any acceptors, at least 1.12 electron volt, which is the energy. Previously I mentioned that one electron volt is equal to 1.6 times 10 to the minus 19 joule. Okay, so this amount of energy is necessary to excite up the electron, or to take out a single electron away from the covalent bond between two neighboring silicon atoms. However, once you successfully dope your pure silicon material with acceptors, not donors, acceptors, then the minimum required energy to break out the covalent bond between two silicon neighboring bonds, then is EA minus EV instead of band gap energy 1.12. Okay? So EA minus EV is, previously there is a table to summarize ionization energy for acceptors as well as donors. So EA minus EV is a few tens of milli electron volt, which is 1/100th of the band gap energy. So way smaller energy is necessary to ionize acceptors. In other words, very small amount of energy is necessary to break out the covalent bond between two neighboring silicon atoms. So that is the magic and power of the why acceptor is necessary. Okay, then at room temperature, here, once all the acceptors are fully ionized, in other words, all the acceptors has accepted, as the word itself has indicated, accepted all the free electrons away from the covalent bonds, then many free holes are created, right? So these holes are kind of a water bubble, okay? So it can freely move or roaming around in the valence band. Okay. So now I hope all of you can draw how dopant atoms are ionized in a pure silicon material, and how come the total number of electron small n is well governed by the total number of dopant atoms. Just here, in this case, the total number of holes created in valence band, right, is fully controlled by total number of acceptors and survey. Definitely, all the acceptors are fully ionized. Because the acceptor is accepting electrons, so it will become negatively charged. Okay. So I guess I have spent about 25 minutes, I guess 25 minutes or so. It is good timing to have a short break time or 1 minute break time. So if you have any question, just leave your message in chatting room, then I'm going to check up. So just 2 minutes break time, just to relax and do not uh, uh, leave your seat. Okay, I have just made a phone call to my teaching assistant, and he said there is no technical issue and there is no help from students. So I guess everything is going well. So we're all well done and well set. Okay, let's keep moving forward. Um, so carrier concentration versus temperature. So on the bottom side, you can see four different energy band diagrams depending on the temperature. So at 0 Kelvin, everything is frozen out, so nothing has been activated electrically. So herein, I guess here many donors are injected into the pure silicon material and no acceptors, right? Because I didn't draw any dotted line close to the valence band edge. So suppose that this material is an n-type silicon material. Then here, small n, indicating the total number of free electrons per unit volume is, 0. Why 0? Because all the donor atoms are frozen out so that no free electrons in conduction band here is not available at all. So no electrons, no free electrons in conduction band. And even the electrons to build up the covalent bonding between two neighboring silicon atoms, those electrons are still frozen out. Okay. So as temperature increases, a few part of the electrons, maybe fifth electron in of donor, I guess this guy, the fifth electron becomes free, and luckily, part of very tiny amount of electron coming from the covalent bonds can become electron because this energy coming from the low temperature cannot be equally distributed out into across the silicon substrate or wafer. Some part of the specific local region of the silicon material can be heated up a lot so that luckily or unfortunately electrons which was to building up the covalent bond can become free so that the free electron will create it from the covalent bond. But most likely, all the fifth electron coming from the donors, this guy, these are three electrons most likely coming from the donors instead of the pure, covalent bonds of the pure silicons. Okay, so in this low temperature regime, the number of free electron is controlled and governed by how many donors are ionized. Okay, so if I n is equal to n sub d plus, but which is smaller than the total number of donors. Okay, so say suppose that half of the donor atoms are ionized, then suppose that the doping concentration is 10 to the 16 per cubic centimeter, then at a certain, usually 100 Kelvin, about 100 Kelvin, half of the donor atom is ionized so that the free electron is half times n sub d, which is equal to 10 to the 16 per cubic centimeter. Okay. And as temperature keeps increasing at moderate temperature, all the donors are fully ionized. So total number of electron is fully governed by donors concentration. But herein, again, still, this electron can add up in determining the total number of free electrons. But I didn't add up, I guess, the number of electrons coming from the covalent bonds should be added up in estimating the total number of free electrons. But I didn't write down this the value of plus alpha. Why is that? Because donor concentration is much greater than the total number of electrons coming from the covalent bonds. Okay, so how to make sure the n sub d is way greater than the alpha? In the previous slide, I said the typical range of the doping concentration is 10 to the 14 to 21. And what is the free electrons available from intrinsic or pure silicon material? That is about 10 to the 10. So compare those two numbers. Okay. So the total number of electrons coming from the covalent bond is always negligible as long as your semiconductor material is doped with acceptors or donors. But definitely the doping concentration should be in the range of typical doping concentration, such as 10 to the 14 to 21. Otherwise, this scenario will not be correct. Okay, and now let's increase temperature more and more at very high temperature. What would be happened? Well, many electrons would come from the covalent bonds of two neighboring silicon atoms. So total number of electrons available is totally governed by how many free electrons, how many EHP, electron hole pairs, are created in this doped semiconductor material. I would claim that the fifth electron coming from the donors would contribute the electron concentration. That's true. However, the total number of electrons coming from the covalent bonds is way much more than the number of fifth electrons coming from the donors, where at high temperature. So at very high temperature, many EHPs are created, and the total amount of EHP is much higher than the donor's concentration. Okay. Then this semiconductor material, even though it's doped with the donors, we can say this is intrinsic. So at moderate temperature or room temperature or at low temperature, still this semiconductor material is doped with donors. That's true. But at very high temperature, electrically, this doped semiconductor becomes intrinsic. Okay? Why we can say that it is intrinsic, it is pure, even though there is donor atoms. Take a look at here, many dotted line here. How come this semiconductor at high temperature becomes intrinsic? That doesn't make sense. It doesn't sound correct. No, it is correct because the number of EHP is much more than the total number of donors. Where? At high temperature. So this whole 1, 2, 3, 4 steps are summarized here in y-axis. My electronic pen is not working. Okay, here, y-axis versus x-axis. So x-axis indicates the temperature in the unit of Kelvin, and y-axis indicates electron concentration n over the donor's concentration n sub d. So here the point of 1 indicates n is equal to n sub d. So at 0 Kelvin, no free electrons, right? So this n over nd value should be here, 0. So at 0 Kelvin, n over nd is 0 here. And as temperature increases more and more, and how this value n over nd varies. Maybe at room temperature, since all the donors will be fully ionized, right? So this would be equal to the total free electrons. So n over nd is 1. So in this temperature regime, right, from say here to here, n over nd is equal to 1. So we can say that this temperature regime is extrinsic temperature region. Okay? So in your midterm and final exam, suppose that your silicon sample is exposed at extrinsic temperature region. Can you guess how many free electrons are available once you dope your silicon sample with a 10 to the 18? Then the answer is, well, because this sample is exposed at extrinsic temperature region, so all the donors should be fully ionized so that total electron, total number of free electron is identical to the donors, the number of donors. So since the problem said 10 to the 18, so electron concentration n is 10 to the 18. That's true. Okay. All right. Then beyond this extrinsic temperature region, say let's move on to the high temperature region here. What would be happen in this region? So as temperature keep increasing, as previously I mentioned, all the electrons to build up the covalent bonds will be excited up because the energy coming from the high temperature is way higher than the bandgap energy, E sub c, 1.12 electron volt. Now you can answer more quantitatively instead of qualitatively. More quantitatively, you can say that if any externally applied thermal energy coming from the temperature is higher than 1.12 electron volt, or in the unit of joule, 1.12 times 1.6 times 10 to the minus 19 joule, then your silicon sample can have tons of electron hole pairs. Okay. More specifically, for your DRAM product and NAND flash product, or even if you use DRAM module in your desktop PC. So maybe I'm expecting very hot summer this year. So because the winter is not very frozen out, so your desktop will be exposed to slightly higher temperature if your air conditioner is down. Then DRAM module would not be working very well. Why is that? The DRAM designer and process engineer has assumed that your desktop will be operating at room temperature. If your air conditioner is not working well, then your DRAM module will be exposed to a slightly higher temperature than the total number of free electrons in DRAM system would not be as expected. Therefore, some wrong operation would be happened. Okay, so you should understand what is the extrinsic temperature region of the material that you are using. Since most of students who are taking my class would be very interested in having a job in SK Hynix and Samsung Electronics company in the end, so that for silicon wise, extrinsic temperature region is about 200 Kelvin up to 400 Kelvin. So this 200 Kelvin regime should be the temperature range at which the DRAM module and then the flash solid state disk should be working operating. Okay, so why? So from this slide, if you can draw the figure shown in the middle, N over ND versus temperature, then you're okay. You're perfect. Okay, extrinsic temperature region. So remember it, and beyond it, even though the silicon material is doped with donors, we cannot say it is doped silicon material. Physically, it has a certain amount of donors, but the role of donors has been lost because of the millions of trillions of electron hole pairs. Okay. All right. Now, let's move on to the next one, electrons and holes. So if you have any question, please feel free to asking it in Korean. I can translate it, interpret it simultaneously, so sequentially, not simultaneously. My TA will handle your question. So leave your text message in chatting window, or just raise up your hand. I guess you can have those functions in your side. We can use those functions. Now, I guess few student has a turned on microphone, not on purpose. So let me. Okay. I have turned off all your microphone by myself. I'm going to share the PowerPoint again. Please make sure your microphone turns off. If you have any question, please leave your message in the chatting window, then my TA will take care of it, and he will let me know what kind of question has been left, then I'm going to answer it. So you can use Korean if it is more convenient. Okay, so let's keep up. See. Okay, electrons and holes in Venn diagram model. This is quite a simple slide. So here, the message that I want to share with you is the meaning of y-axis in energy band diagram. Here, meaning of y-axis. So in all research papers, there is no author to indicate the physical meaning of the y-axis and x-axis of the energy band diagram the author has provided in his or her research papers. Always remember the meaning of the y and x-axis in energy band diagram. Whenever you are taking a look at any type of energy band diagram, the very first job you should do is what is the y-axis, what is the x-axis. In this slide, I would like to tell it. Y-axis plus y direction indicates, as described here, increasing electron energy. So energy of electron, okay, plus y direction. Then, what about the minus y direction? So minus y direction indicates increasing Hall energy. So energy of Hall, okay. Minus y direction indicates the Hall energy is increasing. Plus y indicates the electron energy increasing. Okay, so I guess in a general physics class you may see this kind of equation. The electron's energy is equal to minus q times voltage. Well, if you have some trouble in memorizing this equation, the energy is, in general, we're using the unit of joule. And here, minus q indicates the electron, and V indicates the voltage, volt, right? So one electron volt is actually equal to 1.6 times 10 to the minus 18 joule, but anyhow, joule is equivalent to the electron volt. Okay? And now we are talking about the electron's energy, not Hall's energy, so always minus because the electron is negatively charged. So in energy band diagram, minus y direction indicates a volt. Why is that? Because electron's energy is equal to minus q times V. Okay, so suppose that your silicon sample, its left-hand side is connected to the plus of your battery cell, and right-hand side of your silicon sample is connected to the ground. Then what would be happen in this energy band diagram? Since this energy band diagram, these two parallel solid line indicates, just a band diagram for the pure silicon material at thermal equilibrium. Thermal equilibrium means it will be explained in great detail in next slide. But anyhow, at thermal equilibrium, without any external energy, without any battery, without any power source, you draw the energy band diagram of your silicon material, just two parallel lines, that's it. But what if you applied a certain amount of positive voltage on the left-hand side and negative voltage on the right-hand side? What would be happened in your energy band diagram? The answer would be very simple. Well, if suppose that you apply the 5.5 volt, since this band gap energy is about 1.12 electron volts, so 0.5 is about half of it. So this point would be positioned at the mid. This position, suppose that this is simply ground and no voltage, 0 volt. You can draw it like that. Okay. So now, any band bending happened in energy band diagram is very associated with electrical energy or the voltage that you apply. So all the previous slides, we always seen two parallel lines, which means we didn't use any electrical power cell, didn't use any externally applied voltage. From now on, we will see some banded energy band diagram. Again, we will see the banded band diagram. What does it mean physically? Since you know the meaning of the y-axis, so if there is any difference along the y-axis, always think of any externally applied voltage. Since we are going to talk about the silicon semiconductor devices, we'll see many types of voltage, DC, AC voltage, or step or triangular sinusoidal wave. All those stuff will be applied onto the silicon material. Then, if you need to draw the energy band diagram to understand what happened within your silicon material, please remember the physical meaning of the y-axis and x-axis. So y-axis, okay, energy of electron, downward direction, the voltage that you apply. Remember this equation, right? And what about the x direction? The x direction is quite simple, the physical distance or vector displacement within your silicon material. So this indicates a simply position that you are interested in. Okay. Now let's read out the sentences that I have written. Electrons and holes tend to seek lowest energy positions, which means electron holes would like to have us to take in, just join the lower energy state. Say here is an energy state, here is another energy state. Now this electron has taken this energy state. But in terms of electron's energy, this electron would like to have an energy state at lower energy level, maybe this guy. So this electron would prefer to move downward, right? And then this energy difference will become heat, okay, usually heat. So in energy band diagram, the electrons tend to look for the lowest energy positions available. Okay. What about the hole in energy band diagram? Physics is quite same. The hole is, positively charged carrier, which can flow current, right? Carrier. So electron is negatively charged carrier, flow current. Therefore, the direction-wise, it's direction how those two different carriers are moving. It's quite opposite. Okay? So once hole is seeking a lowest energy position, which means minus y direction is increasing of hole energy. So this hole, there is any empty state here, and this hole would prefer to take this energy state. And this energy difference will be lost as a heat usually. So in energy band diagram, hole is looks like a water bubble, right? Bubble in water bottle. And the electron is like a stone, which is just moving downward. Okay. So without any externally applied energy, electron in conduction band, or specifically free electrons or conduction electrons, which is not the electrons participated in covalent bonds and fifth electron of donors and acceptors, right? Once electron is fully freed out, those conduction electrons, simply speaking, electrons, prefer to seek for the lowest energy state in conduction bands. Then you may guess how free electrons are distributed out in a conduction band. Most likely, almost all electrons would sit down near to the conduction band edge. Similarly, almost all holes would sit down near to the valence band edge, E sub V. So you may have a chance in your undergraduate class, all the electrons are, sitting near to conduction band edge, and all the holes are existing near E sub V valence band edge. Why is that? Because they wanna have their energy state more stable. Energy state more stable, meaning lower energy state they look for. Okay, so we will study how those free electrons are distributed out in a conduction band and how holes are distributed out in valence band. More technically, if I'm using technical words, Boltzmann distribution, and explain how those electrons and holes, those carriers in silicon materials, are distributed out as a function of what? Take a look at the y-axis as a function of energy. Okay, so as a function of electron energy, how many electrons can be found at each specific energy? The question is this: in terms of energy, as a function of energy, at this energy level, how many free electrons are existing? At this energy level, how many electrons can be found? At this energy level, how many electrons can be found here? The number of electron, you can use a symbol small n, right? The number of free electrons per cubic centimeter, right? So this number n can become the function of the energy. Can you find out this analytical equation to connect those two different things? So we'll look for this function in the end. Okay. Okay, so I guess I have spent another 25 minutes. So herein, I'd like to have a short break time. Since now it's 12:55. Let's begin the class at 1 sharp. Okay, so please have a 5 minutes break time, and I will get back to you soon. Just an official announcement, just to double check your attendance. My TA is still checking your attendance, so if you should keep in this real-time lecture room. Otherwise, the server is still checking your connection. So log file that I'm going to download it in the end will tell us how long you are connected in this real-time lecture. So be aware your internet environment and internet status is in good status. Otherwise, it's hard to check what happened in your side. And just in case, my TA is still working on checking how many students are sitting in chatting window and chatting the whole list of the students. So just keep connected and you're safe. And if you have any question, please leave your message in chatting window. You can use it in Korean. Okay, so I will get back to you at 1 p.m. Okay. Um, a few students have some questions in your mind. How can I check attendance? Unfortunately, the headquarter of this university is looking for the log file that we have learned. So your connection history will be left and saved in server. So once I download the log file, I can check how long you are connected in this my WebEx room. So that will be used to double check your attendance. And additionally, my TA is checking how who has attended this lecture. Okay, so I guess I'm going to spend just 10 or 15 minutes more, then we will have a long break time at 15 minutes. Okay, so please keep concentrating what I'm talking. I know it's not easy to, put your 100% of concentration onto your slide. This is online lecture, so it's hard to follow up all the stuffs that I'm talking. So, but please uh, do your best. Okay. See. Yes, so one student has raised up the hand, so let me double check. 삼성 위쪽으로 가면 또 그렇다잖아. 있어 보여야 된다잖아. 저기 조정익 학생, I guess you have raised up your hand, so I have turned on your microphone. Do you have any question? 조정익 학생, can you hear me? I guess 조정익 학생 has raised up your hand. I guess you have used that function. Then a pop-up message has been shown in my side. So if you have any question, leave your message in a chatting window. That's more convenient. Okay, okay, I got it. I guess let me pick up one student and I can turn on the microphone, then ask a question you have. 김권 학생, can you hear me?
네, 들립니다. 예, 들립니다.
Great, great, great. Your device performance of microphone is perfect, so sounds excellent.
예.
The question you have, you know, carrier concentration versus temperature. So as temperature increases, dopant atoms or acceptor atoms are ionized so that we can estimate quantitatively the total number of electrons and holes depending on the doping concentration. So can you understand fully 100% the physical mechanism, how dopant atoms and dopant atoms are critical knob or key in determining the total number of free electrons and holes in silicon material. So, are you with me?
네. 네, 듣고 있습니다.
네, 좋습니다.
예.
That he is with me. Okay, great. And let's see. Amin, am I correct? Amin, student. Amin,
Yes.
are you online? Can you hear me? Great. Do you have any question? Do you have any question?
No, right now.
No. Okay, great. Let me see. Let's pick up one more student. This is funny and interesting. 소진이 학생. Do you have any question? Some noisy sound has come in. Now it's okay. Any question?
아직 없습니다.
아직 없습니다. Okay, great. No. Let's talk with one more student. 석준아 학생. Do you have any question? He's not online. 석준아 학생, can you hear me? I guess he's doing something else. 석준아 학생, can you hear me? Hey, TA, 태건이. Turn on. 태건이 학생, 태건이 TA. Hello. 김태건 학생 어디 갔어? Where is he? Okay. 이가은 학생, can you hear me? 들리세요? 는 학생은 도대체 무엇을 하고 있을까요? Technical issue or something? Pick up one more student. 구지환 학생, can you hear me? So, what happened? 송민준 학생, can you hear me? No microphone. I guess your laptop doesn't have some small microphone. Then I cannot hear it. You know. Okay. Minjung 학생 can hear me. He doesn't have a microphone on his side, so that's okay. No problem at all. Pick up one more. The last person. 오동현 학생, can you hear me? No. He doesn't have microphone. Okay, no problem at all. Yes, he has tons of concern how to access my lecture room, but he has in the end successfully connected to my room, so no problem. And I guess you made it. Okay, great. Okay. All right. Let's talk about some the thermal equilibrium more. So the physical meaning of thermal equilibrium is quite simple. No energy coming from outside, then we can say that we are at thermal equilibrium. So as described in this lecture note, no external forces are applied, which means you are at thermal equilibrium, or my silicon sample is at thermal equilibrium without any external force, such as electric field, means no voltage, and no magnetic field, no mechanical stress, and no light. Say DRAM and NAND flash memory, those chips are well packaged so that light cannot get into the DRAM chip and NAND flash memory. So usually light is not a big problem in a memory module. What about the mechanical stress? Well, since a DRAM module is connected, wirely connected into the PCB board, and that PCB board has been inserted into the main board of the desktop or notebook. So mechanical stress wise, it doesn't have it is less likely for DRAM module on PCB board to be exposed to the mechanical stress in real situation, maybe in server, in your desktop, notebook, even in smartphone. All the package is a solid state, so I guess there is no chance to see mechanical stress. What about the electrical field and magnetic field? Definitely, there are tons of different amount of electric field and different amount of voltage, magnetic field as well. So electrical field and magnetic field, electromagnetic class in undergraduate class, right? So EM, electromagnetic class, you may have a chance how those two fields are working together. But in this lecture, semiconductor devices, since we are going to externally apply electric field, in other words, we are going to use a certain amount of DC power. So electric field is a main, key force to be applied in your semiconductor devices. Okay, so on the second bullet, you can see the dynamic situation in which every process is balanced by its inverse process, which means, for example, let's think about how electrons and holes are created at room temperature, not at 0 Kelvin. At room temperature, free electrons are created and the same amount of holes are created together because they are occurred in pairs. I'm talking about the pure silicon material. Then the total number of electrons and the total number of holes are identical, which is equal to the n sub I. That was 10 to the 10 per cubic centimeter for silicon. Now question is as follows. 10 to the 10, 10 billion. 10 billion electrons, you can line them up. The first electron, 10 to the 10th electron. So these specific electron can be alive forever in silicon material as a free electron. The first electron out of 10 to the 10 electrons is existing as it is once it is created. Yes or no? Maybe you students, yes. The other student, no. The answer is no. Why is that? Because the very first created electron would be existing, say, for 1 second. After 1 second, that electron will be annihilated. It will be killed, recombined with the other holes, so that the very first created electrons can never be alive forever. Why this kind of process has been happened in silicon material? Because at room temperature, the externally applied thermal energy has been supplied to the silicon material so that all the electrons and holes are dynamically affected by the external thermal energy. So electrons and holes are moving around, roaming around, and they're gonna hit to each other and lose its energy, or in some cases it will gain more energy. So electrons and holes would have some possibility to become free or to become annihilated, to become recombined with the other counterparts. So in this second bullet, you can see that electron hole pair generation rate should be equal to the recombination rate. Then we can keep this 10 to the 10 number. Otherwise, EHP generation rate is slightly higher than the EHP recombination rate. then the number of free electrons keep increasing as over time. Okay? So over time, the total number of electrons and holes should be well kept at room temperature as 10 to the 10. However, within a silicon material, dynamically, the very first created electrons in the end would be annihilated, and a very new electron, I would say, 10 to the 10 plus once new electron has been created. Okay, so this situation is named as a dynamic situation. Okay, so in dynamic situation, all the process, all the mechanism, all the things happened in the silicon material is well balanced by what? By its inverse process. For example, once electron hole pair is created, then at some other location, at other position in a silicon material, electrons and holes are recombined together. Then the total number of electron holes are well stable. At room temperature, the number of electron holes are identical to the 10 to the 10 per cubic centimeter. Okay. Okay. So let's move on to the third one, thermal agitation. So thermal agitation, that is another word of thermal, energy. So once externally applied energy is smeared into the silicon material, and thermally silicon material is agitated. So agitated, if I say agitated, in Korean, it's a 휘졌다, I guess. Thermal agitation, excitation, thermal excitation or agitation. Yeah, both are okay. So thermally agitated silicon material would have some possibility in which electrons and holes can give and take its own energy to each other, even with a crystal lattice. So crystal lattice means silicon atoms. Okay. Going back to the bonding model, this electron has become free, and in the end, it is moving around, and it would hit the silicon atom. Then this thermally agitated energy will, exchange with a lattice or silicon atom. Okay. Okay. So, the last arrow here, saying that in at thermal equilibrium, in crystalline silicon material, every energy state in conduction band and valence band, so draw the energy band diagram again here, E sub C and E sub V. All the energy state in conduction band and valence band, each energy state has its own probability of having electrons. In other words, the probability of finding out free electron at a certain energy state here and there, there is the probability value of finding out electrons. However, physically, most likely electron would prefer to have a lower energy state. So the at this energy level, the probability of finding out the electron is quite high. But maybe at very high energy state, say this guy, the probability of finding out single electron is super low. Okay? So every energy state in a conduction band and valence band has a certain amount of probability of finding out electrons, or certain amount of probability of being occupied by an electron. Okay. All right, that's a basic concept of thermal equilibrium. And this slide shows an analogy for thermal equilibrium. So this is quite simple. This is a conduction band H, and there are many energy states in conduction band. So each energy state, you can find out electrons, but here the analogy is like this. There is a dish on the vibrating table, and the sand particle is matched to the free electrons. So table should be stabilized, is in a good stable status. However, now table is vibrating, which means external energy is now supplied to this table, so the table is now vibrating. In other words, in silicon material, the thermal energy, in other words, at 300 Kelvin at room temperature, silicon wafer or silicon substrate or crystalline silicon material has been exposed to the thermal energy. Then, in its conduction band energy, all energy state, there is a probability of being occupied by electron. Okay, so that then previously I mentioned that at lower energy state in a conduction band has a higher probability value of finding out the electron, because the electron would prefer to have a lower energy state. But at higher energy state like this, there is the non-zero probability of finding out the electron. However, the probability value itself is quite low compared against the probability value at lower energy state. So that kind of things happened in conduction band of pure silicon material is quite well matched to the sand particles in dish on vibrating table. So that this slide would like to give you some intuition and insight how to understand free electrons in silicon material has been distributed out in its conduction band. Okay, and here one key message is there exists a certain amount of probability, non-zero probability, for the electrons in conduction band to occupy a high energy states at thermal equilibrium or under the agitation of thermal energy. Okay, so that is the concept of the thermal equilibrium. So let's have now what time is it? 1:25. So I'm going to resume my lecture on 1:40. Okay, so please have a break time of 15 minutes, then I will get back to you. 1:40 again. Hey.